Hello everyone. Right now I am going to present to you our project for machine vision and how it is intended to help with interstate highway traffic safety. Um, this document is prepared by me, Matthew Williams, and listed underneath are all of the group members that also participated with me in completing this project. Let me first show you a output video of our project, and then I'll discuss how it works. So in this video, you'll see that we identify the vehicles on the road and we check to see whether it's a car, a truck, or a motorcycle. We also try to determine its speed and what color the vehicle is. This line down here is called a line zone, and it has a in and an outside. And whenever one of these object bounding boxes collides with it, it will increase a counter and count for that object crossing this line. So I'll let the video play out and maybe have it get back a little slower than normal, just so you can see. As you can see, the speeds though are not correct at all, and that was one item that we're trying to fix. And in our document, we ran this on four different camera feeds, and we checked to see how close we are with the counts. So you can see with the colors, we got the white here, and that's largely due in part that the pre-trained model, when it draws the bounding boxes, it includes the trailer part of the truck as well. So even though the cab is yellow, majority of this is white. We got ourselves this black car here, another black car. Majority of the vehicles are either black or white. We could go to another video. This is I think the next 30 seconds. And this is one part where the pre-trained model also is a little confused because it recognizes this as a truck, trailer truck. However, since this pickup truck is hauling with a hitch behind it, a trailer as well, it also classifies this as a semi-truck. And we are aware of some misses. I'll go over that in the document. Some more footage of the traffic, and you can see the count as they increment when these vehicles pass by. This one seems to be having trouble when trucks are passing by on this end here. or when the bounding boxes, the classifier isn't sure yet and it flashes. So I'm thinking when it's flashing, because it's unsure, it's crossing and it doesn't detect because it believes it doesn't see an object. So the first video clip, though, is by far the best one to showcase the counter, because the accuracies on these later clips definitely took a dip in comparison. So we'll go through the code here. Um, so this was ran in Google Colab, and all of the data was moved over into a folder. So we have our 3 camera IDs and then our video ID. This was just so we could cycle through and run them consecutively. Uh, these are the constants for our line zone, so the start of the line zone and the end of the line zone in its XY coordinates. Here's our path to our videos, and then we selected to only use look for these 3 classes, a car, motorcycle, and truck, in the videos, and we're using Ultralytics, their full data set, so it has a ton of different labels in there, but we want to just filter down to these 3 for our use case. We do, of course, our imports and our model. We're using the 8X model. That's the uh, most powerful model Yellow has, and then putting all of those model names in a dictionary for further use. These settings here is just for the video path. To get some info, we need to get the frame rate for calculating the speed when we try to. This pixel to feet ratio was a calculation that I had written a Python script for, and I could show it at the bottom. So here's the quick script. I used a still image and I set some points down. That's this point 1 and point 2. So these lines are these dashes are supposed to be 10 feet long on all roads. And so with these 2 points, we could then basically calculate how much distance 1 pixel represents, and that's what this is supposed to be. So 0.3 feet per pixel. However, due to this camera perspective, you could see that 1 pixel further away from the camera represents a great deal more distance than a pixel closer to the camera does. This green line is our horizon line. It was some additional attempts made to help with the speed calculations, but they were still not coming out correctly. So we'll go back up to the top, continue where we left off. So we got some dictionaries to kind of store previous values for later computation. So the smooth speeds is to average out the previous frames and this frame's current frame's speed. Same thing for the previous positions. It's used in the same manner. The byte tracker, this part there could be a lot of different configurations that I we attempted to changing frame rates, changing these conservative frames. This is supposed to be so when something goes out of frame, uh, that the annotation sticks to the object um, for a few frames before just disappearing. That was trying to help with the annotations, the bounding boxes and labels from flashing. These are all of our instance and frame generators, the line zone annotator, our label annotator, the boxes, the dot annotators here, but not used in this current form. It was another attempt for calculating the speed. Here is the some of the speed calculations. We have a 5 frames is supposed to average over. So the first method to get called is the calculate speed, which then uses the get perspective scale, and that uses that horizon, that green horizon line I showed earlier. And these calculations here were provided through just a simple Google search for converting this frames per second to miles per hour. Next is for identifying the colors. What we ended up doing was creating a range. So red can be between these ranges, blue between these ranges, and so on. So then when the average of all the pixels in the bounding, a subset of the bounding box, if the average fell between any of these ranges, then the vehicle gets classified with this color. This is the main loop, the demo callback. So here's our detections set up. So that's all of the detections. And then this line is just the detections for only our selected classes that we had, the car, truck, motorcycle. These are all loops. In this loop here, this is, for every frame it loops. So in this one here, we actually get the center of the bounding boxes, and then we crop into it, and then that cropped portion is what gets sent to the color method. We had to do this in order to get rid of the bounding boxes, which showed over the road. So one example of that is like here, you see, here's a good example of this truck. It's right now saying its color is gray, but you can see this huge bounding box here, and more than half of it is just the road. So it doesn't work well with these trucks because the center point is here, and so when we crop in, you still have some of the gray area there. And if you crop in too small, then you may end up on like a windshield, front windshield, back windshield, and then it's going to classify as black. So there's some issues with this method, but it was the one that kind of worked best for our purposes. Here's a good example of the color classifier encountering some issues at first until the right perspective or enough lighting is present for it to pick up on the color. So as you can see here, this vehicle is clearly red, but the classifier says it's black. I'm going to slow down the playback speed, and I'll hit play. As it gets closer to the camera, you will notice that it does correctly classify as red. So right there. I am not sure why from this point to this point it decided it was black to red. I could only imagine that either the bounding box, the center shifted back a little bit, so then more of the roof and side of the vehicle were present during the average pixel color calculations, or the lighting. Maybe there's some more lighting got reflected off of the body of the vehicle so that the reds were more pronounced in the RGB values. But this, I would say this clearly does show that our color classification does work. So in this loop, we go over every single of the tracked detection objects that we found, and this does in zip, so it basically makes a dictionary for us by zipping together these items with these items. We have to first check to make sure that the box center is actually there, and then we see if it's the tracker ID, which is a assigned value from the byte tracker. I'm not sure how they just assign the IDs, but it gives the ID to every object. So we are using that to see if it's has a previous positions, and if it does, then we're then able to calculate the attempt to calculate the speed based off of the previous position and the current position with our calculate speed method. So we pass in the previous position, the current position, which is the center, how much time has the elapsed, which is 1 over the frame rate, and then that ratio that we calculated earlier with the center point of the box, and then the image height, and that's required for the horizon distance measurements. Then we get the color. And this is constructing our label. So if the vehicle's new, we can't really give it a speed because we don't have a previous position on it. So it only gets a tracker ID, vehicle classification type, our confidence levels, and a color. If the color can't be determined, you may have seen it, it'll say NA on it in the videos. Then we package this all together into these annotated, on the annotated frames. And then this is line updates the line counter, so its trigger is on every detections. So every detection it is to increment the counter on whether it's on the in or the out facing side. This is the loop that gets ran that calls all of this above. That is all of our code. So I'll go to the document to review results. So in our 4 different videos, GT stands for ground truth, MV stands for machine vision, and human counted for ground truth. So we're just hoping that there's no errors in the ground truth counts. But you can see we had 10 in, 17 out, and then machine vision counted 6 in and 17 out, so it was 100% accurate on the out counts and missed 4 on the in, the accuracy of 85%. Then, as you can see later on, it drops off a lot, and I think that's due to on videos 2, 3, and 4, we had a lot more trucks, and those seem to not trigger the line zone counter as reliably as a car does. So there is definitely more details about our project and issues we encountered with the speed and color in the report. I would like to cover the acknowledgments for NDOT and then specifically for the rest of my team members for their contributions to the project and the code. All right, thank you very much.